Welcome back to my channel Experience of Physics. The topic for today's lecture is electrical power and energy, right? And also Joule's law of heating. Electrical power and energy. So we will discuss the Joule's law of heating also, right? Let me take one conductor of resistance R and I am connecting a battery to it, V volts. So this battery will send one current, say I amperes. Right. So current is nothing but flow of positive charge. So this point we have studied under the topic drift velocity. Current is nothing but flow of positive charge. This Q and V, this product, Q and V is called as work done. Under the heading electric potential, we have established this relation, right? Work done in moving one unit positive charge is known as electric potential. Work done in moving one unit positive charge is known as electric potential, 1 volt. So if you cross multiply it, you will get QV is equal to W, work done. This product, QV is W, IV, this product, I into V is called power, P. I into V is called power, right? So let us relate these two formulas, work and power. Work done by the battery is also known as energy spent by the battery, right? So this is power and this is energy. First let me write the formulas for power. P is equal to V into I. Power P is equal to V into I. From Ohm's law, I can write V is equal to, or I can write I is equal to V by R. I is equal to V by R. This is giving me V square by R. This is another formula for power. P is equal to VI or P is equal to V square by R. Right. Again I can write V is equal to I into R. From Ohm's law, V is equal to IR. Right. This gives me I square R. P is equal to I square R. So P is equal to VI or P is equal to V square by R or P is equal to I square R. Any of the three formulas we can use to calculate the value of power. So if V is varying, V square by R. If I is varying, I square R. If both are varying, P is equal to V into I. So this QV is equal to W or energy. To mean energy, let me write E here. Work or energy. Work or energy. Work done or energy spent, right? W or E. Q, we will write I into T. I is equal to charge by time, so Q is equal to I into T, V. So this is E. V into I into T. I am grouping V into I. VI is equal to P. PT is equal to E. So the energy is nothing but power multiplied by time. Energy is equal to power multiplied by time. That is the relation between power and energy. So these formulas we have established for the calculation of power. If I multiply it with time, we will get energy. So here energy is equal to VIT. This is the first one. Energy is equal to VIT. Then energy is equal to V square R into T. Then third one, energy is equal to I square R into T. So the unit of power is watts. Unit of power. Unit of energy is watt second or joules. Unit of energy is watt second or joules. Watts second, right? So these two formulas are enough for us to establish all these 6 formulas. Q into V, work done, already we have studied it. V into I is power, right? V into I is power. Then we can relate all the formulas which are required for the calculation of power and energy, right? So let us take few problems and understand how they are done, right? So this is Joule's law of heating. E is equal to I square RT, E is equal to V square by RT, E is equal to, this is Joule's law. Joule's law of heating. Yes. Right. An electric bulb, when connected across a power supply of 240 volts, consumes a power of 160 watts. Right. This is the bulb. It is connected with 240 volts. It consumes 160 watts. If the supply drops to 180, right? Instead of 240 voltage, the battery value is coming down to 180. If the supply drops to 180, the power consumed will be what? What is the new power? Instead of 160 watts, what is the new power of consumption of the bulb, right? If it is reduced, so this is the rating of the bulb, 240 voltage. If 240 voltage is maintained, 160 watts, the brightness will be proportional to the 160 watts. If it is reduced, the brightness level will be reduced. Dimness, the bulb will glow without the full intensity, right? So that is the idea. So we have to find first one, the resistance, because the resistance is constant. Irrespective of the voltage what we are giving here, the resistance value will not change. It is constant. So find the resistance first. R is equal to V square by P. Original voltage, rating 240 into 240 divided by P is 160. So this will be 2 into 8, 3 into 8. So this is 120. 3 into 120 is 360 ohms. The resistance of the bulb is 360 ohms. It is constant. Then the new power. For the reduced voltage, the voltage is reduced to 240, instead of 240, 180. 180 into 180 divided by 360. So this is 0, 18, 36, 90. We will get only 90 watts. Instead of 160 watts, 90 watts will be the answer. 90 watts. So if we reduce the voltage rating of the bulb, we will get the power consumption low, right? We will not get the full intensity of the bulb. A bulb of 50 watts, 10 voltage is operated at 100 voltage supply. 100 voltage supply. The rating of the bulb is 10 volts, but we are increasing the voltage. Right? In the previous problem, we have reduced the voltage, but here we are increasing the voltage. If the bulb glows with full intensity, then the value of resistance to be connected is. So, the bulb requires only 10 voltage. Bulb rating is 50 watts, 10 voltage. 10 voltage is enough for the bulb. But we are giving 100 voltage here. So what will happen to this case? If we increase the voltage, what will happen? Because the R value is fixed, right? I is equal to V by R. R is fixed. I is proportional to V. If we increase the voltage, the current will also increase, right? Say for example, in this case, what is the R value? Let us find the R value. V square by P. The rating is 10 voltage. 10 into 10 divided by P is 50. So this is 2 ohms. The R value is 2 ohms. The bulb has the resistance value of 2 ohms, right? The 10 divided by 2 is equal to 5 amperes. Only 5 amperes. But if we give 100 voltage here, the 100 divided by 2 will be 50 amperes. Isn't it? So in this case, the bulb will not be safe. The more current will burn the bulb. The filament will be burnt, right? So this is not advisable to operate the lower rating bulb with a higher voltage. So in this case, what people will do is, they will connect a series resistance here to drop the excess voltage. Excess voltage is 90. The bulb requires only 10. The excess voltage is the remaining voltage, which is nothing but 90. Yes. Now we can safely operate the bulb, right? Because its resistance is 2 ohms, 50 watts, 10 voltage. The resistance we have calculated it as 2 ohms. R value is 2 ohms, right? The I value, 10 divided by 2 value will be 5 ampere. The current is 5 amperes. Already we have found some, yes, 5 amperes. 10 divided by 2. In series circuit, the current will not change. So 2 ampere is flowing through the resistance also. Now the resistance value of the series resistance RS is to be found. The question is to find the value of series resistance. V by I, Ohm's law, V by I. So 90 divided by R is equal to, the current value is 5 ampere, right? Not 2 amperes. This is 5 amperes. 5 ampere current in series circuit, the same current is flowing through the resistance also. So 90 divided by 5 ampere, 18 ohms. So we have to connect 18 ohms resistance in series with the bulb. Then the bulb will be safe. We can easily get the full intensity because 50 wattage will be the power consumption of the bulb. Safe, right? So in the previous case, we have reduced the voltage. If we reduce the voltage, the brightness level of the bulb will be reduced. If we increase the voltage, the brightness level won't change, but it is not safe for the bulb. So we have to drop the excess voltage by adding one series resistance. That is the question here. Here, 3 bulbs of 40 watts, 60 watts and 100 watts are designed to work on 220 volts mains. Which bulb has the minimum resistance if they are connected in series with 220 volt supply? 3 bulbs, their power rating is given 40, 60, 100 are designed to work on 220. All the 3 bulbs have same voltage rating, 220. 220, 220, 220. The designed value is 220. Which bulb has the minimum resistance? Minimum resistance if they are connected in series. If they are connected in series with the 220 voltage supply, right? Bulb 1, bulb 2, bulb 3, we are connecting with 220. Which bulb has the minimum resistance if they are connected in series? See, type of connection will not change the resistance value. Resistance value is fixed. It won't change, right? Unless the temperature is changed, we have studied under the topic temperature dependency of resistance, right? If we don't change the value of temperature, the resistance will not change, right? But here the question is, if they are connected in series, which bulb will give the minimum resistance? The type of connection will not change the resistance. So resistance is constant, whether it is connected in series or parallel, right? It never change the value of resistance, right? So 40 watts, 60 watts, 100 watts. So P is equal to, this is the formula. P is equal to V square R. The rating is same, 220, 220, 220. All the 3 bulbs will have the same rating, 220. Right? So P is inversely proportional. From here, let me write what is R. R is equal to V square by P. So R value we want to find, minimum resistance. So R is proportional to 1 divided by P. So the minimum resistance, which bulb is having the minimum resistance? To have the minimum resistance, the power rating has to be more power rating. The answer is 40, 60, 100. 100 watts. 100 watts is the answer. So 100 watts bulb will have the minimum resistance. Yes, this problem. For the circuit shown in figure, the current must not exceed. So 3 bulbs are connected in series. 1 by 4 watts, 1 by 4 watts and 1 watts. This is 250 kilo ohms, 10 kilo ohms and 10 kilo ohms resistance value. Voltage rating is not given, right? Power value and R value is available. P1, R1, P2, R2, P3, R3. Voltage value is not available. To find the current, we need voltage. First, let us find the voltage value. So P is equal to V square by R. From here, I will write V square is equal to P into R. V is equal to square root of P into R. For the first bulb, V is equal to, or let me write V1 here to denote it as first bulb. P1 is 1 by 4. R value is 250 K. 250 into 1000. So this is 4 and this can be written as 250. Then this is 250 into 250 inside the square root. So 250 voltage. Second bulb, V2 is equal to P into R. P value is 1 by 4. R value is 10K, 10 into 1000. Then this is 250, which can be written as 10 into 250. Let me write it as 25 into 100. 10 into 250. Then this is, if we remove the square root, 25 will become 5 and 100 will become 10. 50 voltage. For the second bulb, for the first bulb 250, second bulb 50. Then the third bulb, V3 is equal to, power value is 1 watts, this is 10K R value, 10 into 1000, 10 into 1000, 10,000, so 100 voltage. V3 is 100, V2 is 50, this is 250. Then I1 is equal to V1 by R1, V1 is 250, R1 is 250K, so the current is 1 milliamperes. So that is the safest current, right? Because the R value is more here, you can easily find I2 also. I2 is equal to V2 by R2. V2 is 50, R2 is 10K. 50 divided by 10 is 5 milliamperes. This is 10 to the power of 3, and 10 to the power of minus 3. For 10 to the power of minus 3, straight away you are written as milli. And I3 is equal to 100 divided by 10K. K, 10,000. So this will be 10 milliamperes. So the answer should be the lowest value. Lowest value is the safest value. 1 milliampere is the answer. The current must not exceed option A, 1 milliamperes. Right, this one, interesting. How many 60 watts bulbs may safely be run on 220 voltage supply using a 6 ampere fuse? So fuse is one element which is used in a circuit to protect the circuit. Right? This is the fuse. This may be some bulb. Fuse. This is V, and this will send one current I to the bulb. The fuse will protect the bulb from excessive current, right? The fuse, usually the fuse will have high melting point. Low melting point. Low melting point. That means immediately it will melt, right? Immediately, whenever excess current flows through the fuse, it will melt immediately. Also, it will have high resistance. It will have high resistance. So the current rating will be put accordingly to protect the applicant devices. So bulbs, right? So the maximum current for the bulb is 5 amperes. The fuse rating will also be 5 amperes. Right? If any current which is flowing more than 5 amperes, the fuse wire will get burned. So then it will disconnect the bulb from the supply. The supply and the bulb will be disconnected, right? The materials used for the fuse are tin, lead alloys. So tin, lead alloys, they have high resistance, low melting point, right? So here, how many 60 watts bulbs may safely be run on 220 volt supply using a 6 ampere? That means some bulbs we are connecting, we don't know how many bulbs can be connected here. But the current rating is the fuse rating. Using a 6 ampere fuse means the maximum current which can be sent through the circuit is 6 amperes. So this is 220 voltage. How many bulbs? The bulbs ratings are 60 watts, 60 watts, 60 watts, right? Don't assume that it is a disconnection here. This is a continuous circuit, but some lamps are connected in between them, right? 220 is voltage rating, 6 ampere is the current rating. So power is equal to 220 into 6. V into I will give us the power rating of the circuit. Power rating of the circuit, right? The power rating of each bulb is 60 watts, right? Then the number of bulbs is equal to total power divided by power of the bulb. Total power is 220 into 6 divided by power of the bulb is 60 watts, right? So this is 0 and this is 6. 22 is the answer. 22 such bulbs can be connected in the circuit which can be operated safely. 22. The answer is 22. Yes. The next one. In the circuit given, if the power dissipation is 150 watts. In the circuit given, power dissipation means power dissipation of the battery is 150 watts. Then the value of resistance is what? What is the value of resistance? So the power dissipation of the entire circuit is 150 watts. What is the value of R here? To find the value of R here, we need current through R and the voltage across R. Then we will use the formula V by I. So voltage across R is available between the 2 points, 15 voltage is available. So V is equal to 15. The current through R has to be found. How to find it? Right. So this is 150 watts, right? The total current we can easily find. 150 is P is equal to V into I. This is 150. V is 15 into I. Then I is equal to 10. 10 ampere is the current which is flowing from the battery. Up to this point the 10 ampere comes. It is divided into 2 branches. V divided by this 2, this resistance will also have 15 voltage across it. So 15 divided by 2, 15 divided by 2 is 7.5. 7.5 ampere is divided here. It is flowing through the 2 ohms resistor. Then the remaining current, which is 2.5 amperes. This current is 2.5 amperes. 2.5 amperes because it is 10 amperes. 7.5 amperes takes this branch. So 2.5 amperes must go through this R. The V is known, now I is known. 15 divided by I. R is equal to V by I. So 15 divided by 2.5. So this is 6 ohms. Yes, option A. 6 ohms is the answer. In this circuit, when certain current flows, the heat produced in 5 ohms is 4.05 joules. 4.05 joules. 5 ohm resistance. So 6 ohms and 9 ohms are they are in series. The series is parallel with 5 ohms. Again the 2 ohms comes in series for the entire combination. The heat produced in joules in 2 ohms. What is the heat here? In 2 ohms resistance. In the same time, the time is constant. The time is constant. So this is given in joules. Heat is equal to energy is equal to power multiplied by time. It is 4.05, right? Power value is I square or T is equal to, let us assume the same time interval is given. So let me assume T is equal to 1 second. assume T is equal to 1 second. So this will be heat H is equal to I square R T. This is 4.05 I square. R value is 5 ohms. Heat produced in 5 ohms. 5. Let us assume T is equal to 1 second. I have assumed T is equal to 1 second. So this is 5 I square. Then I square is equal to 4.05 divided by 5. This will be 8 5s are 40 and 1, right? So this will be 0.81. 8 5s are 40, 1 5 is right. I square is 0.81. Then I is equal to square root of 0.1 will be 9 into 9, 81. So this will be 0.9. I is equal to 0.9 amperes. So that means the current through this 5 ohms resistance is found. This is 0.9 amperes. So using the heat data, we have found the current through the 5 ohms. Then the 0.9 into 5 will give the voltage across this 5 ohms resistance. 5 into 0.9, this is 4.5 voltage. This 4.5 voltage is appearing across this 15 ohms. This combination is 15 ohms, right? So this current I can easily calculate. This is 0.9 amperes. This current, say this is I2, this is I1. I1 0.9 amperes. Using this 0.9 amperes, I have found the voltage across it is 4.5 voltage. Then the 4.5 divided by 9 plus 6, this is 15 ohms will be the current I2. 4.5 divided by 9 plus 6. 4.5 divided by 15 is 0.3 amperes. So the total current is this current I. So because we are interested in finding the heat value, I square RT I have to put here. So the current there is 2 ohms I have to find. Now the two currents are now found. We will add the two currents I1 plus I2 is equal to 0.9 plus 0.3, 1.2 amperes. 1.2 ampere is the total current here. 1.2. Then I square RT. Heat is equal to I square R into T. I square is 1.2 square. R value is 2 ohms. And T already we have assumed for this case 1 second. The same time interval. 1 second we have to put here 1.2. 1.44 into 2. 2.88 joules. 2.88 joules. 5.76, 2.88, yes. 2.88 joules is the answer, yes. Yes, if the coil of a heater is cut into half, what would happen to heat produced? Coil of heater. Coil, so resistance, this case 1, cut into half. Half of the resistance is here. If it is R, then this will be R by 2. Voltage. Half of the resistance is now here. What would happen to heat? H, voltage is common. H is equal to power into time. Power is equal to, since voltage is common here, let me write power is equal to V square R into T. V is common, T is also common. So heat is proportional to 1 by R. So first case, let us find the ratio H1 to H2 1 by R. So this will be R2 by R1. R2 is R by 2. Then R1 is first case R. H1 by H2 is equal to R and R are cancelled 1 by 2. So H2 is equal to 2 into H1. The heat will be doubled. Heat will be doubled. If we use half of the resistance, the heat will be increased. Right. A constant voltage is applied between the two ends of a uniform metallic wire. Some heat is developed. If the length of the wire is doubled, and the radius is half, the heat developed is, if we change the length and the radius of the conductor, what will happen to the heat? That is the question, right? So length and radius, these dimensions of the wire, they are affecting the resistance directly, because R is equal to rho L by A, we know. If length is changed or radius is changed or area is changed, the resistance value will be changed. So the question is to find the heat after the dimensions are changed, right? So heat is equal to V square R T. Heat, V common, T common. So heat is proportional to 1 by R. H1, this ratio, H1 by H2 is equal to R2 by R1. Inversely proportional. R2 by R1. R2 by R1 rho L2 by A2 divided by rho L1 by A1. The rho is removed. So this ratio is L2 by L1 multiplied by A1 by A2. The length is doubled. The length of the wire is doubled. So L2 by L1 ratio is directly given, but the area is not directly given, only the radius is given, right? The area is equal to pi R square. So area is proportional to R square. So from here I am writing A1 by A2 is equal to R1 by R2 square. R1, the radius is half. So R1 is 1, R2 is 1 by 2, half. So this is 1, 1, 2, this will be 4. So this ratio is 4. A1 by A2 is 4. Then L1 by L2. So here we need L2 by L1. Yes. L2 by L1. This ratio L2 by L1 is, the length is doubled. The length of the wire is doubled here. So this is 2 by 1. So let us put here. 2 by 1 is put here and 4 is put here. 2 by 1 into 4 is equal to 8. So H1 by H2 is equal to 8. So the question is the heat developed after changing the dimension. The new heat H2 is equal to 8 H2 is equal to H1. So H2 is equal to 1 by 8 H1. 1 by 8 times it is reduced. 1 by 2, this is 1 by 8 times it is reduced. This problem. In the two circuits shown, all the light bulbs and batteries are identical. A, B, C. The bulbs and battery, light bulbs and battery are identical. Same voltage rating, same power rating. All the three bulbs. Similarly, the battery values are also similar. If A, B and C respectively denotes the brightness of bulb, brightness A, B, C here. the bulbs A, B and C respectively denotes the brightness of light bulbs A, B and C. Then C is greater than A is equal to B. C is less than A is equal to B. C is equal to A greater than B and C is equal to A less than B. Right. Power rating, voltage rating same for all the three bulbs. Look at here in the first circuit, the short circuit is important. The short circuit will make all the current from the battery to flows through it. The entire current supplied by the battery will be flowing through the short circuit. So here the current value will be 0. No current is flowing through 0 amperes. No current is flowing through the bulb B. So the bulb will not glow. The bulb will not glow. So immediately we can get this point. So the B value, the brightness of the B value will be the lowest one of the equation. Less than, it is equal, wrong. A is equal to B. A greater than B, wrong. This one must be the answer. So among the 4 options given, the option C, the brightness level of the B is low here. C is equal to A, let us check. C is equal to A, yes. One battery connected with A, one battery connected with C, right? So C is equal to A is also true. Because this battery, the positive terminal is connected here, the negative terminal is connected here. The entire V voltage will appear across here. 0 voltage is appearing across this bulb B. So 0 divided by this resistance will be 0 amperes. No current flows through bulb B. So the bulb will not glow here. Here 4 bulbs B1, B2, B3 and B4 of 100 watts each. 100 watts each. Yes. Each rating is 100 watts. Connected to 220. 220 voltage mains, right? So all are in parallel. All the bulbs are in parallel. The reading of an ideal ammeter will be, the reading of the ideal ammeter will be what? That means current through this line is asked. Ideal ammeter means it has 0 resistance here. We can have a short circuit. Instead of this ammeter, we can have a short circuit. Through the short circuit, what is the value of current which is flowing through it? So that is the question. Right? So this is parallel. V value is given, power value is given. Power is equal to V into I. I is equal to P divided by V. P is equal to 100. V is equal to 220. So this is 10 divided by 22, 5 divided by 11. This will be 5 divided by 10 is equal to 0.5. It will be less than 4 into 11 or 44. So this will be 0.45 amperes. So I is 4.45 amperes. Current through each bulb is 0.45 amperes. V, P is given. So directly we are getting the current. So same rating, voltage is also same, power is also same. This is 0.45. This current is also 0.45. 0.45. All the 3 currents 0.45, 0.45 and 0.45. All the 3 are joining here and they are flowing through the ammeter. 3 into 0.45 will be the answer. 1.2, 1.35. 1.35 will be the answer. Yes. if voltage across a bulb rated as 220 volts, 100 watts drops by 2.5% of its rated value, then the percentage of rated value by which the power would decrease is 220 volts, 100 watts, this is the rating of the bulb. It is dropping down to 2.5%. The voltage rating 220 volt is dropped. Then the percentage of rated value by which the power would decrease is how much reduction in the power, right? So 2.5%. So in such problems we can use the method of error analysis. Method of error analysis. Less than 5% is the change. If it is less than 5%, we can directly apply method of error analysis. So 220 volts, 100 watts, voltage is changing. So P is equal to V square by R. V is constant. Now V is changing. So P is proportional to V square. R is constant. Voltages across the bulb is drops. This voltage is 220 voltage is change. 2.5% is the change. So P is proportional to V square. So from here, using method of error analysis, I will write delta P by P is equal to 2 into delta V by V. Square root 2. It is like differentiation. dP, both sides if you differentiate it, 2 into delta V, right? So delta V by V is 2 into, the reduction is 2.5%. So the answer is 5%. 5% is the answer. Right. The same mass of aluminium is drawn into two wires, 1 mm and 2 mm thick. So 2 wires. Two wires, 1 mm and 2 mm thickness. Thickness means diameter. It is thickness, diameter, right? The two wires are connected in series and the current is passed through them. Series connection. Current is passed through them. Heat produced in the wire is in the ratio, right? H is equal to V square by R, isn't it? This formula we should not use here. Important. Why? The two wires are connected in series. This is wire 1, this is wire 2. This is voltage. They are connected in series. So here current is same. Voltage is not same. Voltage is divided here, right? So we should not use this formula. So H is equal to I square R formula we must use here, right? So H1 by H2, H is equal to, H is proportional to R, H1 by H2 is equal to R1 by R2. Same mass is same. Aluminium, material is also same. Mass same, material same. So mass, if mass is given in such problems, immediately you must bring the volume point here. Material is also same. That means the density is also same. So mass divided by density is equal to volume. If mass is same and material is same, so mass and density are same. then volume is same. This point will be useful for us to relate the resistance here. H1 by H2, R1 by R2. R1 by R2, rho L2 by, this is L1. L1 by A1 divided by rho L2 by A2. The rho removed, so this is L1 by L2 into A2 by A1. So here the thickness is given, the thickness is affecting the area value, right? Area value, right? Then L1 by L2, no hint about the L1 by L2 is available. Lengths are, no such point is directly given about the lengths, but this point is important. Mass is same. So since mass is same and material is same, we are finding the volume is same, right? So volume same, for same volume we will write volume same, we will write L1 A1 volume, L1 A1 is equal to L2 A2. So L1 by L2 from here, L1 by L2 is equal to A2 by A1. L1 by L2 is equal to A2 by A1. If I put here, L1 by L2 is A2 by A1 and A2 by A1. So this is A2 by A1 square. Then A2 by A1. Diameter is available. Thickness 1 mm and 2 mm. Diameter is available. Area directly we will find. H1 by H2 is equal to A2 by A1 square. H1 by H2, A2 by A1 square. This is pi by 4 D1 square. A2 is D2 square. D2 is 2 mm. D2 is 2 mm into 2 square. Pi d square by 4 divided by 1 mm. So 1 square. Again it is squared. D square, then this square. D square, right? So pi by 4 are removed. So this is 4 by 1 square. 4 by 1 square. So this is 16 by 1. So H1 by H2 is 16 by 1. Option B. Okay. Similar problem. The same mass of aluminium, material same and mass is same. Drawn into two wires, 2 mm and 3 mm thick. Thickness means it is diameter is given. The two wires are connected in parallel and the current is passed through them. Two wires are connected in parallel. In the previous problem it is in series. But here in this problem it is parallel and the current is passed through them. Heat produced in the wires is in the ratio, right? So here it is parallel, so I will use this formula. Not I square R. Parallel connection V square by R. So H is proportional to 1 by R. Voltage is common, parallel connection. So H1 by H2 is equal to R2 by R1. The same way we will write rho L2 by A2 divided by rho L1 by A1. Rho let us remove. This is giving us L2 by L1 into A1 by A2. So A1 by A2 pi d square formula we can use 2 mm 3 mm. L1 by L2 or L2 by L1 we will relate the mass. Mass same, material aluminum. So volume is constant. Volume is same. Since the volume is same, we will write L1 A1 is equal to L2 A2. L2 by L1 is equal to, this will be L2 by L1. L2 by L1 is equal to A1 by A2. So instead of L2 by L1, I will write A1 by A2 into A1 by A2. So this is A1 by A2 square. The same procedure like the previous one, right? So H1 by H2 is equal to A1 by A2 square. A1 is pi by 4 d square. First one 2 mm. d2 square divided by pi by 4 d1 square divided by d2 square. Yes. Pi by 4 we are removing. So square also, yes, square. d1 square divided by d2 square square. d1 is 2 mm. So 2 means 2 square 4 divided by d2 square is 9. 3 square is 9 square. Yes. This will be 16 divided by 81. The answer is 16 by 81. 16 by 81, option A. Only thing is, we have to start the problem from here. H is equal to V square R. In the previous one, we have started from here. H is equal to I square R, not V square by R, because it is series. Yes. Heater coil A takes 15 minutes. Coil A takes 15 minutes to boil certain quantity of water. Heater coil B takes 30 minutes to boil the same quantity of water. Coil A takes 15 minutes time. Coil B takes 30 minutes time. Same quantity of water. If A and B are connected in parallel, they are connected in parallel, the time taken to boil the same quantity of water by the combination, then A and B are, so in the earlier case they were used separately. Coil A separately used to boil some water. The same quantity of water coil B is used. Coil A took 15 minutes, coil B took 30 minutes. If they are put together, combination, both the units, what is the time taken to boil the same quantity of water? What is the time taken to boil the same quantity of water by the same source? Yes. Heater, time is given. So H is equal to power into T. So this is the formula we can use here. So time is related with heat with the factor power. H is equal to P into T. H is common in both the cases. The time is varying, right? So H is equal to, let me write PA here, 15 minutes. 15 PA. So it will give PA is equal to H by 15. Then here H is equal to PB into 30, isn't it? Coil B takes 30 minutes, power into time. So PB is equal to H by 30. Then both the powers are used combinedly, coil A and coil B. That means power A and power B both are used together to boil the same quantity of water. That means same heat is required, right? Same heat is required. The H value will not change. Same heat, PA plus PB. Both the heaters are combinedly used. This is the new time, T new. So we will PA, we will write H by 15 plus H by 30 T new H, which is 30 2H plus H T new 3H by 30 new time. H I am removing. This will become 10. So 1 by 10 T new. So T new, this side 1. So 1 by 10. T new is equal to 10 minutes. 10 minutes is the answer. 45 minutes, 10 minutes. So first separately they are used to get the same heat, HH. Then they are together used. An AC generator of 220 volts having internal resistance R is equal to 10 ohms and the external resistance R is equal to 100 ohms. What is the power developed in the external circuit? Yes. This is the AC generator. Internal resistance R is equal to 10 ohms and external resistance R is equal to 100 ohms. What is the power developed in the external circuit? What is the power developed here? This is internal. The generator and the resistance are internal components, right? This is the external circuit. This is the external circuit. So first we have to find its rating is given 220 volts. Yes, 220 volts. 220 volts. First we have to find P is equal to I square R formula we can easily use. P is equal to I square R. R is available, P is in question. So I has to be found. I. So it is 220, this is R, this is 10 ohms, this is 100 ohms, it is 110 ohms. 110 ohm is the resistance, total resistance, 220 divided by 110 ohms. So 2 ampere is the current here. 2 ampere. Then the external circuit power is equal to 2 square into R value is 100. So 400 watts. In the external circuit only 100 ohms. You should not include here, right? So 400 watts. Answer is option B. Yes, a current of 3 amperes flows through 2 ohms as shown in the figure. The power dissipated in the 5 ohm resistor is what? If 3 ampere is flowing through 2 ohms, what is the power dissipated here? Power dissipated P is equal to I square R formula we can use. 5 ohm is available, R value, then I square. This current has to be found. What is the current flowing through this branch? So to find the current flowing through this branch, we need the voltage across it. Between these 2 points, what is the voltage? If this voltage is found, then V divided by the 6 ohms, 5 plus 1, series connection, 6 ohms will be the current, then we can apply this formula, P is equal to I square R, right? So all are parallel connection, 3 into 2, 6 voltage is the voltage. So 6 voltage, 6 voltage, 6 voltage, this is 6 voltage, then 6 divided by 6 ohms is equal to 1 ampere current. 1 ampere current. The current through this branch is 1 ampere. Then 1 square into 5 ohms, 5 watts. The answer is 5 watts. 1 watts, 5 watts. Option B. In the diagrams, all light bulbs are identical. All are identical. All cells are ideal cells. That means no internal resistances. And identical. Their values are same. Ideal means they don't have any internal resistance. Identical means the voltage rating is same. Same voltage, same voltage, same voltage, right? In which circuit will the bulbs be dimmest? Right? The dimmest, most dimmer, right? In which circuit? The bulbs are glowing uniformly. In which circuit? A, B, C, D. In which circuit the bulbs are dimmest? Right. Let us assume the voltage is V here. So V. So combinedly 2 voltage is there. Since all the batteries are identical, let me assume the value is 2V. V, then it is 2V. Then this is V, this is V, this is parallel connection. Look at it. Parallel connection. Then only V is applied here. Here it is series connection 2V, 2V. So look at the polarity also. Right? The polarity is minus and plus are unlike polarities are connected here. So I am adding them. So this is also 2V. So this is V. Parallel connection. So to increase the current capacity, people will connect the battery in parallel. To increase the voltage rating, they will connect it in series. To increase the current rating, they will connect it parallel, right? So this is V, this is 2V, 2V, 2V. Bulbs are also identical. That means 2 voltages available in this circuit. Identical 2 bulbs are there. So the 2 bulbs will share the voltage equally. V and V. V and this is also V. This bulb gets V voltage. Similarly, this is also getting V. Here it is 2V, 3 bulbs. 2V by 3 it is getting 2V by 3. So 2V by 3 is 0.67V. So 0.67V is only available for each bulb. This is V. They are dividing equally. So V by 3. V by 3 is 0.33V. 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 Then this is 2V. 2V, 2V parallel connection. So the question is, in which circuit the bulbs are glowing dimmer? So this is V and this is 0.67V, this is 0.33V, this is 2V. The bulbs are getting only 0.33V. So option C is the answer. The dimmest bulbs are in option C. Bulb B1 100 watts 250 volts and bulb B2 100 watts 200 volts are connected across 250 voltage in this manner. What is the potential drop across B2 is what? Across B2 what is the voltage? Potential drop, right? So this is 250 voltage. The 250 voltage shared between the bulbs B1 and B2. So the voltage sharing can be easily calculated if the resistance are found. So I am going to draw this circuit this way. This is the resistance of bulb 1, this is the resistance of bulb 2, 250 voltage. R1 we can find, R1 is equal to V square, V1 square divided by P1. V1 is 250 into 250 divided by P1 is 100. So this is 25 into 25, 625 ohms. R2 similarly, P2 square divided by P2, V2 is 200 V2 square, so P2 is 100. So this is 400. So R1 is equal to 625, this 400 ohms. Then these two are in series, the current will be found, the current into 400 will be the V2. So I is equal to, first we will find I 250 divided by 625 plus 400. 625 plus 400, 1025. 250 divided by 1025, 5 table or even 25 tables. If it is 1000, this will be 1.4. 1025 is available. If it is 1000, 1 by 4. It is 1025, so this will be 4.1. The current value is 1 by 4.1 amperes. Current through the circuit is 1 by 4.1 amperes. Then into this resistance 400, right? So voltage across bulb 2, let me write here V2. V2 is equal to I into R2. 1 divided by 4.1 into 400. 400 divided by 4.1. If it is approximated as 4, 400 divided by 4 will be 100. Approximately this voltage is 100. So we need an answer which is closely coming to 100. 200, 98, 250, 48. 200, 250, 98. 98 is coming closer to 100. So 98 is the answer. Right. Two electric bulbs marked 25 watts, 220, 25 watts, 220 and 100 watts, 220. Two bulbs. Their voltage rating and power rating are given or connected in series, right, to a 440 voltage supply. Which of the two bulbs will fuse? Two bulbs are connected in series to a 440. Same are having similar voltage rating, right? Voltage 220, bulb 1, bulb 2. 220, 220 voltage. Power is 25 watts and this is 100 watts. Both are connected in series across a 440 voltage supply. Voltage is common. Which of the two bulbs will fuse? So current rating has to be found. Current rating. The lowest current rating bulb will get fused immediately, right? For that, so R is equal to V square by P. This relationship will give us the R value. Voltage is common, so R is inversely proportional to 1 by P. So here less power, more power. So power value is low here, power value is high here, 2500. So R value will be more here, R value will be less here. R is inversely proportional to P. Then Ohm's law, I is equal to V by R. I is indirectly proportional to R value. So I is less here, I is more here. So this is the bulb which has low current rating. So this bulb will get fused 25 watts. This bulb will get fused immediately, first, right? 25 watts is the answer. So no need of making any calculation. Just by comparison we can find the answer. Right. Three identical resistors are connected across a voltage source V, so that one of them is in parallel, with others, with the two others which are connected in series. Right. So three identical resistors, let us say R ohms and R ohms, R ohms. The first one is coming in parallel with the other two are in series, connected in series. The power dissipated through the first one compared to the power dissipated by each of the other two is. Each of the other two. This power divided by this power or this power divided by this power. This is asked. Let us say this is V voltage. Yeah, V voltage is given. Voltage source V. So power dissipation, let us use this formula I square R. This current and this current separately. So this is, say this is I amperes. Let us say V by R is equal to I. V divided by R. Right. Then this current will be V divided by 2R. This current, right? V divided by 2R is the current. V by R is I, then this is I by 2. So it carries I by 2 amperes. This resistance carries I amperes and this branch carries I by 2 amperes. Then power P1 divided by P2 is equal to I square R divided by I by 2 square R. R removed, I square removed, we will write it as I square divided by I square by 4. Then this is 4. P1 divided by P2 is equal to 4. The power dissipated through the compared to the power dissipated by each one of them. So P1 is equal to 4 P2. The power dissipated through the first one compared to the power dissipated by each of the other two is P1 is equal to 4 to 4 times is higher. The same twice as much, half as much, 4 times as much. Right. Two wires A and B of same material and same mass have their lengths in the ratio 1:2. L1 by L2 is 1:2. Mass and material are same. This point already we have discussed here. Material same means density same. So mass by density is equal to volume. Volume is same. So this means volume is same. Right. What is the question? On connecting them to the same source in parallel, the rate of heat dissipation in B is found to be 5 watts. The rate of heat dissipation A is what? Right. So heat is equal to power multiplied by time. Heat is time, same time rate of heat dissipation. So we can write H1 by H2 is equal to power. Power is inversely proportional to resistance because P is equal to V square by R. Isn't it? P is equal to V square by R. Same source in parallel. So this is P is inversely proportional to R. H1 by H2 is directly, it is equal to P into T. So this is R2 by R1. H1 by H2 is equal to R2 by R1. Rho L2 by A2 divided by rho L1 by A1. Rho's are removed. So this is L2 by L1 into A1 by A2. Here using this point, we the length ratio is given, area is not given. So L1 same volume is same. So L1 A1 is equal to L2 A2. We want A1 by A2. A1 by A2 is equal to L2 by L1. L2 by L1, let me put it here. L2 by L1 instead of A1 by A2. So this is L2 by L1 square. L2 is 2, L1 is 1. So 2 by 1 square. So this is 4. So H1 by H2 is equal to 4. H1 by H2 is equal to 4. H2 is given, I think. Oh, A and B, right. 1 is A, 2 is B. On connecting them to the same source in parallel, the rate of heat dissipation B is found to be 5 watts. So H1 is 20 watts, or coil A, heater A, 20 watts is the answer. Yes. If current flowing in a conductor changes by 1%, current is changed to 1%, then power consumed will what? Again we will use the method of error analysis. So power is equal to, since I is changed, we will use this formula, I square R. P is directly proportional to, because same conductor, we are not changing the conductor, we are changing the current value only. So P is proportional to I square only. Delta P divided by P is equal to 2 into delta I by change in power, change in current. So 2 into, this is 1%. 2% is the answer. Yes, 2% is the answer. Two heater wires of same resistance are first connected in series and then in parallel. The ratio of the amounts of heat produced in the two cases will be, right? First they are in series, then they are in parallel. Two heater wires are same resistance, R value, R value, R value, R value, V, V. So the equivalent value is 2R. The equivalent value is R by 2. V is common. Heat dissipation. Heat is equal to power into T. The heat is proportional to P. The P is equal to V square by R. So P is inversely proportional to R. The ratio of amounts of heat produced. So H1 by H2, I will write R2 by R1. That is, second case is parallel. R parallel divided by R series. R parallel is R by 2, the equivalent value, this is 2R. So this is 1 by R, 1 by 4. R and R are removed, 1 by 4 is the answer. 1:4, option B. Yes, this is assertion reason. What is assertion? Fuse wire must have high resistance and low melting point. High resistance and low melting point. Yes, true. Fuse wire must have high resistance so that its current rating is low. Low melting point. Quickly it will burn. It should burn. Reason? Fuse is used for small current flow only. No. For all applications, fuse wires are used. Small current, medium current, high value of current, right? So this is true. This is wrong. Both assertion and reason are wrong. Both means it is not the right answer. Assertion is true. Reason is false. Reason is false is also true. Both assertion and reason are false, wrong. So option C is the right answer, right? So this is the last example of this video lecture today here, viewers. Thank you for watching. Best of luck.